we learned about model selection and complexity control in general. We also learned about radial basis function and neural network. And I'm going to make what we have learned about complexity control more concrete in terms of mathematics behind this notion. And then we will see how this can be more precisely applied to radial basis function, complexity control, model selection, as well as neural network. Okay? So I'm going to talk about model selection today, or complexity control. So selection or complexity control. Recall that, I told you that usually we have an underlying function f, but we do estimate a function given data, which we call it f hat. And we would like our estimate to be close to the true function, but there is always a relation between bias and variance. Bias squared plus variance would be mean square error. Okay? So that's what we would like to minimize, but depends on the complexity of the model. We are either decreasing the bias but increasing the variance, or vice versa. We feed a line to our data, say for example in regression. It's high bias but low variance. But we feed a polynomial of degree n-1 to n data. It's very high variance, but it's low bias, right? And we need to have basically a trade-off between these two and find minimum mean square. Okay, I'm going to define T to be a set of data. Say I have n data point. This is my training set. I assume that each data point, yi, is f of xi when f is true underlying function plus some noise. Okay? So this f is true function and epsilon is some noise. So we are assuming that it's Gaussian noise centered at 0 with a standard deviation sigma. Okay? So I assume that the noise is additive noise. In terms of notation, now f hat will be my estimated function. And f hat of xi, I call it y hat. Okay. Also, for simplicity, sometimes I use fi, and I mean f of xi, and I would say f hat I, and I mean f hat of xi. Okay. So usually, we have this training set. We feed a function to our data, and this function gives us some y hat, right? And we are minimizing an objective function when this objective function is basically summation over yi's and yi hats, right? This is usually what we minimize as our objective function. This is our empirical error. And we had this discussion in the previous lectures that this empirical error, always decrease, but true error decrease up to some point and then start to increase. And the optimal model would be a model which has minimum error on the, minimum true error, not minimum empirical error. That's our empirical error, and minimum true error is different from this. Okay? Okay, so in practice, that's the objective that we are usually trying to minimize, which is biased downward. It's not a good estimate usually of the true error. It's biased downward, and we would like to take care of this bias somehow. Okay, given this point, if I write this quantity, expectation of y hat minus y. This is, y is my observation. Y hat is when I feed a function to the data and I estimate some, I have some prediction. And in the process of minimizing the empirical error, that's one of the terms that I'm minimizing. If I look at the expectation of the term that I'm minimizing in empirical error, let's more closely look at this term and see what this term that we are minimizing is and what does it mean. This is a y hat that I estimated from data, and y is f plus epsilon, right? There's a true function that has been distorted by some noise. Okay, that's my observation y. So my observation y is basically f, the true function, minus epsilon, the noise. Okay. So I will write it as y hat minus f minus epsilon squared. So I just group these two in one group, minus epsilon. And now it's a squared, so it is y hat minus f squared plus epsilon squared minus 2 epsilon y hat minus f. Okay? Okay, now this is expectation of y hat minus f squared plus expectation of epsilon squared minus 2 expectation of epsilon y hat minus f. Okay. This is my estimation. This y hat is my estimation. So y hat is basically f hat. It doesn't matter if it's just, let me just write it f hat. So that's my estimation. That's the true one. This is basically what I need to minimize. See? What I need to minimize is the distance between true function and estimated function. But in empirical error, what I minimize has other terms as well. I'm minimizing the true error plus two other terms. So if I really would like to minimize the true error, I have to take care of these two terms somehow. Because I don't have access to f. F is unknown, right? So I do have access to this quantity. So left-hand side of this quantity is known. If I can estimate these two quantities, then I do have an estimate of the true error. So let's see if we can estimate these two terms. So expectation of epsilon squared. What is it? It's just sigma squared, right? Because epsilon was has normal distribution, centered at 0, and the standard deviation was sigma. Okay, what about this term? Is it 0? Why it's 0? Fixed with respect to
this x0 is given, so y0 have they are fixed, they're just constant. So this is that term is the expectation of epsilon. So it's the mean of epsilon.
It might be more clear, this is y hat. If I tell you that this is f hat, this is my estimation. If I change epsilon, f will not change, right? F is true function. What about f hat? If I change the noise of the data, does it change my estimate or it doesn't? No? I give you this data and tell you to predict a line for me. I add the noise. Now predict a line for me. It doesn't change your estimate? It does change your estimate. If I change the noise of the data, I have a new set of observation, and I do estimate my function using my observation. So changing the noise will change my observation, will change my estimate. Okay? So I can't say that this term is 0. In general. In some cases it is, but not always. Let's consider, different cases more carefully. So case 1. In case 1, I assume that this data is not in the training set. Okay? So I was looking at empirical error of a given data point, and this data point, suppose that is not in the training set. If this data point is not in the training set, that you are right, that this term is 0. Because I estimate my function using my training set. And I have an estimate f hat here. I'm talking about y0 or y null, which is not a part of this. It doesn't matter how much I change this y. It doesn't matter how much I change the noise of this y. It's not even a part of endpoints that I use to train my model, It has nothing to do with the model that I estimate. So this cross term will be 0 if if this y null is not a part of the training set. Okay? So this cross term in this case will be 0. To say it more, clearly, can say that this epsilon is basically, in fact, this epsilon is y minus f. So it is y minus f, and this is f hat minus f. And this yi is not in the training set. And f is constant, is a true model. And this is an estimate which has nothing to do with this y hat, because y hat is not in the training set. So this is going to be 0. It's like covariance of y and f hat. And these are independent now. F is independent from y. So this is going to be 0 in this case. Okay? So it's going to be 0 in this case. So any questions so far? Is it clear? Okay. So, so since it's 0, I can say that expectation of this expectation squared is equal to expectation of f hat minus f squared plus sigma squared. And the third term is 0. Now, that was for 1 point. If I sum over m points, but these m points are not a part of training set. I just choose m points that are not in the training set. If I sum over m points that are not in the training set, then basically I have summation of all yi hat minus yi squared, I equal 1 to m, is equal to summation of fi hat minus fi squared plus summation of sigma squared. Okay? So the summation of sigma squared, sigma is constant, so it's just m sigma squared. Okay? This is the error that I was looking for, the distance between true function and estimated function. Let me show it by this notation. And this is my empirical error. The error that I can basically is distance between my observation and my estimation. But in this case, I choose points that are not part of the training set. I have already trained my model. Then I introduce points that are not in the training set. And my model has some prediction for that. And I'm looking at the distance between prediction and y. Okay? So let me call this, show it with this notation. So here we had our notations. Let me add these two. This is my true error. And this is my empirical error. So this basically tells me that true error is empirical error minus m sigma squared, which is a constant. Okay? So in other words, empirical error is a good estimate of the true error up to a constant. In this case. So in this case, it means that I would like to minimize the true error. But suppose that I minimize empirical error. That's okay. Because it's an estimate of the true error up to a constant. So if I minimize this, it's as if I minimize this, because this constant has nothing to do has no effect in my optimization. I'm trying to find a model with optimum complexity. So if I go for optimum complexity that minimize this quantity, I can assure you that it has been minimized this quantity as well. This is the main justification behind cross-validation. In cross-validation, we are training a model using training set. But when we want to decide about the complexity of the model, we are checking this with a validation set. Do you remember? That was our training set, where we took a part of data, we set it aside, call it validation set. Okay, and this is the training set. And we are learning the model using this, but we are testing the model using validation set, data that model hasn't seen so far. And we are trying to minimize the error here. So when you're minimizing the error here, your estimation, your empirical error, is a good estimate of the true error. So if you have a model which minimizes your validation error, then you have minimized the true error. Okay? So this is the main justification for cross-validation. So the more interesting case would be the case that this data is in the training set. So quite often we are minimizing training error. And that's where overfitting happens, right? Because it goes down all the way when you add the complexity. So let's see what's happening in this case. So in the case that this data is a part of training set. So when this is a part of training set, everything goes fine, except that this cross term is not 0 anymore, right? So basically, our question is that can we estimate this cross term? Okay. So can we estimate this? Any idea? Yes.
Use the estimation of F hat, but we can put epsilon. In this case, we can extend calculate the expectation.
So basically, you are assuming that there is a closed form for f hat in terms of epsilon, but it's not the case in most of the time, right? And most of the time, you don't have closed form estimate for f hat. You have a neural network, and the output is just some f hat. You can't write it in a closed form. Even in the cases that you can write it in closed form, it's not in terms of epsilon. You know, I feed a polynomial. It's not in terms of epsilon. So this estimation is not trivial. Okay. We have to use Stynes Lemma to estimate this. So what is a Stynes Lemma? Basically, it says that if there is a random variable x, let me write it here. If there is x which has normal distribution, theta sigma squared. And suppose there's a function g, and this g is differentiable function. You can take derivative of this function. Actually, it's enough if it's weakly differentiable. So if you have this, then expectation of x minus theta gx according to Stynes lemma is just sigma squared expectation of derivative of g with respect to x. Okay. So x is normal. This has normally distributed. X minus the mean of x times g, and g is an arbitrary function, but the condition is that you can take derivative of g. If you want to compute this expectation of product of these two terms, when one term is normally distributed and the other one is a function of this random variable, then this expectation is sigma squared when sigma was standard deviation of this normal, and expectation of derivative of this g with respect to x. Okay? Okay, let's apply this Stynes lemma to our problem. Our problem is to estimate this basically cross term here. So how can I apply Stynes lemma here? Tell me what would be, if I just want to apply this lemma here, what would be my g, what would be my x? Sorry?
Gx should be f0 hat minus f0.
Okay.
And then x minus theta
Is epsilon. Right. So basically, you know, this is my epsilon, because epsilon was normally distributed, centered at 0. So this is basically epsilon minus 0. Right? And then G is this term, because f hat is a function of epsilon, right? So f hat minus f is this G. So this is my G, and this is my x minus theta. See, I mean, f hat is a function of this f. F is not a function of epsilon, but f hat is. So f hat minus f is a function of epsilon. Okay. So according to Stynes lemma, this is going to be sigma squared expectation of G, derivative of G, which is f hat minus f, with respect to x, with respect to epsilon. So this is sigma squared expectation of derivative of f hat with respect to epsilon minus derivative of f with respect to epsilon. So what's derivative of f with respect to epsilon? It's 0, because f is independent from epsilon, right? So no matter what your noise is, it doesn't change your underlying function. Underlying function was a function prior to your observation, right? Observation was the true function disturbed. So it doesn't matter how much you disturb it. You know, the true function was true function. So they're independent. This is 0. So this is sigma squared expectation of derivative of f hat with respect to epsilon. So I can go one step further. I just write a chain rule here. This is f hat. I would say with respect to y, my observation times y with respect to epsilon. Okay, what's this second term? Derivative of y with respect to epsilon. Just remember that y was f plus epsilon. Now, derivative of y with respect to epsilon is derivative of f with respect to epsilon, which is 0. Derivative of epsilon with respect to epsilon is 1, right? So derivative of y with respect to epsilon is 1, which makes sense because derivative means I perturb this variable, how much this variable is going to change. So y is f, which is a constant plus epsilon. I perturb epsilon, I change my noise. How much my variable, how much my observation is going to change? Exactly the same, you know, because it's constant plus the noise. So you change the noise, exactly the same your observation will change. So I can write my cross term as sigma squared expectation of derivative of my estimation with respect to observation. This is an interesting term in terms of concept. derivative of my estimation with respect to observation. Suppose that this is my observation, and my estimation is just a linear function. This is my f hat. So this term means I perturb one point. I change one of these points. How much my estimation will going to change? Okay. Consider this case when my estimation is a linear function. With this case, I have the same set of points, but my estimation is not a linear function. It's quite a complex function. It goes through all of this point. If I perturb one point only, I have to see how much my estimation will change due to this perturb. I do the same thing here. I change this point to this point. Do you think this quantity is going to be larger here or larger here? Larger for the complex one, right? So in this case, that my function is a complex function, if I perturb a point, my estimation will change a lot. When it's not a complex one, it's a low complex function. When I perturb a point, my estimation doesn't change much. So you can think of this as a measure of complexity of the model that you are fitting. Okay? So let's call this D. So D is just this derivative. Derivative of estimation with respect to observation at a particular point. Okay. Now, yes?
Does that also mean that as you have more sample points, if you have more samples, the degree to which each one influences your final estimation gets smaller, right? So does that mean that we get closer to the actual error if you have more data as well?
If you have more data, your estimation, your final estimation, will be more robust.
Right.
But I'm talking about, our estimates, point estimate, my estimation at a single point.
Right. So that.
Yeah, if I write the summation over all of these points, basically I need to compute the summation over all points of this quantity.
Right.
How much, if I perturb each of these points separately, in total, how much my model will change.
So it's independent of the sample size, that rate of change?
It is not independent of the sample size. But I think you can directly conclude that if your sample size is large, this quantity is going to be small.
Right.
Okay. But it's not independent. So in this case, that was the quantity that originally we start to work with. So we have this term. This is true. This corresponds to true error. We have this term, and we didn't know how to calculate this cross term, and now we know what this estimation is. So basically, this is going to be this term plus sigma squared minus 2 sigma squared this quantity. Now let's sum over all points, say n points. But in this case, all of these n points comes from training set. So we sum over all n points where these points are from the training set. So summation over all points here actually would be sum I equal 1 to n of yi hat minus yi squared is equal to sum over all points of f hat minus f squared plus summation I equal 1 to n of sigma squared, which is n sigma squared minus 2 sigma squared summation of di, where di is just sigma of fi hat with respect to yi. So this is a measure of complexity. Okay, let me just use the notation that I used before. So this is my empirical error. This is my true error. This is a constant. This is not a constant anymore. This is a function of the complexity of the model. So when it was not a part of training set, I didn't have this term. So minimizing this was the same as minimizing this, because that was constant with respect to the complexity of the model. Now I have a term which is not a constant with respect to the complexity of the model. So this goes up when the complexity goes up, right? So the true error is empirical error minus a constant plus 2 sigma squared, a function of complexity. This is called Stynes Unbiased Risk Estimator. In short, they call it SURE, Stynes Unbiased Risk Estimator. So it is Stynes Unbiased Risk Estimator. So it is SURE. So can we estimate the cross term? Sure. Okay. So see when, it gives you now a very good insight that why we have this behavior. Empirical error, when empirical error is training error, when we are using the data points that we have seen in the training set, goes down all the way when you add the complexity of the model. So this is always decreasing. This is constant. I even don't care about it in terms of minimization. But this goes up when complexity goes up. With low complexity, it's small. With high complexity, it's large. So I have this function plus a function which has completely the opposite behavior. It's a small here, it's large here. So this part has a behavior like this. And together, together they have this behavior, This is what we observe about the true error, that up to a certain model, it goes down and then it starts to go up. It starts to goes up because of this quantity. Because there is a function of complexity which is going to contribute to the true error. Okay? And that's why we observe this. Any question? Yes.
So the empirical error could be larger than the true error when a model is not very complex.
The true error, the empirical error could be
Larger than the true error.
no, because you have this constant as well, It's always biased downward, When model is not complex, it's pretty small. And you have empirical error minus, some value would be the true error. Yeah, the true error, you are saying the empirical error could be larger, yes. Yes. Okay. So it is interesting theoretically, but it gives us some indication or some direction how to go for complexity control and find the optimum number of optimum complexity in some case. So in particular, I'm going to show you how can we use SURE or Stein's Unbiased Risk Estimator to find the optimum complexity of radial basis functions. Okay? So let's get back to RBF, radial basis function, and see how can we compute the optimum complexity. So recall that the complexity of RBF is controlled by the number of radial bases, right? So the more nodes that we have, the more complex the model is. The less node that we have, the less complex the model is. We had this discussion in the previous lecture that these nodes can be roughly interpreted as mixture of different Gaussian. As you have more Gaussian, you're modeling your data with more Gaussian compared to less number of Gaussian, for example. But in general, it contributes to the complexity. So we had, W in terms of phi, and we had, but if you just remind me what was these values that we computed in the past. We had this as input, x1 to xd. Then we had m phi, that was phi 1, that was phi m. And we had some output. And if you remember, we defined x to be like d by n of our data. And then phi was m by n. And then we had y, which was like k by n. And we had w, which was m by k. Then we computed w in terms of by minimizing y minus w transpose phi. Using least square, we computed w. What was that w? phi transpose inverse, phi y transpose. Okay. So that was phi transpose. That was phi. Okay. So that's our W, right? If this is my W hat, sorry, my Y hat is going to be W transpose times phi, right? So my estimation in this model is W transpose times phi, which is Y phi transpose phi transpose inverse transpose times phi. So to get rid of this inverse transpose, let me transpose both sides of this equation. So Y hat transpose is phi transpose phi transpose inverse phi Y transpose. Okay, that's my estimation, you know. That's F hat. This is my observation. What radial basis function does is to estimate the function using this equation. And this equation, you can see that it's linear, you know. This is a linear transformation on Y. So you give me Y, I apply a linear transformation on Y, and I give you Y hat. Okay? Because phi is just constant, right? So I decide about the number of nodes. I decide number of nodes to be 2, to be 3, to be 10. I decide about number of nodes, and then I compute this phi for every data point and put it in this n by n matrix. Then I compute phi transpose inverse phi. This is a transformation. Now I apply this transformation to my Y, to my observation. Let me call this transformation H. So Y hat is H times Y. When H is just constant here, right? Okay. You know, Y hat, we have K outputs. For simplicity, let me assume that I have only one output. Then you can see that if you want to extend it to K output, that would be trivial to extend. So let's assume that the number of output nodes K is equal to 1. So I have only one output node. So in this case, this y hat, which was k by n, is going to be 1 by n. And I had, sorry, a transpose here. So, and the y hat transpose would be n by 1, right? So it is a vector now. I just write it this way. So y transpose is h y. Is that clear? I just assume that we have one single output. So this matrix is, which was k by n originally, now it's 1 by n. 1 by n is not a matrix, it's just a vector. I just changed my notation, you know. You can still keep your notation, just I thought it's more convenient to, or more clear to explicitly show that it's a vector, it's not a matrix. Okay. So suppose that I want to apply, sure, Stein's unbiased risk estimator. I want to estimate the true error of RBF. The true error would be empirical error minus n sigma squared plus 2 sigma squared 6 sum over di, when di is just derivative of fi with respect to yi. This is my fi hat. This is my estimation. So if I want to apply sure to RBF, I have to take derivative of my estimation with respect to one data point. Okay? So this is y hat, or this is my estimation. So I would like to apply sure to RBF, and I need to compute di, which is derivative of fi hat with respect to yi. So what would be what is fi hat in RBF? You know, this is n by 1 vector, which is the estimation of all of my n data point. For data point number x, for data point I with index I, for xi, or for observation yi, what would be my estimate? You know, I have this n by 1 vector, which is just h times y. Y is n by 1, and this h should be n by n. You know, this h should be n by n. Phi is m by n. Phi transpose is n by m, m by n. And this is phi, phi transpose, m by m. So h is n by n. Okay? So I have this n by n matrix h times n by 1 vector y. It gives me n by 1 estimation by hat. So what would be fi? Means what would be this particular estimation? Sorry? The i's rho of I times yi, right? Sorry? You are talking about the derivative. Yeah. Okay, so basically fi hat which is shown by yi hat as well, would be this row, means row number I of H. So I show it with this notation. It's like MATLAB notation, row I, all columns, times y. It's a vector. And this is scale. Now I need to compute di, which is derivative of this fi hat with respect to yi. Basically, I need to compute derivative of h I all columns times y with respect to yi, with respect to one of the elements of this vector. What this derivative is going to be. Let me write it this way. The hi times y means this row times this column, right? It is basically hi1 times y1. This element times this element. This element times this element. Plus hi2 times y2. Plus hii times yi. Plus hi plus 1 times yi plus 2. Plus hi, the last one, n times yn. I would like to take derivative of this with respect to yi. It's going to be hii, right? So everything will be 0 except, they're not dependent on hi except this one. So when you make this multiplication, no one has any effect except that the corresponding element on this row of H. So this is hii. I mean, di is hii. So let me write sure for this case. The true error is empirical error minus n sigma squared plus 2 sigma squared summation over I to n of hii. Okay, what is summation over, summation from I to n of hii? It's trace of h, right? So the true error is empirical error minus n sigma squared plus 2 sigma squared trace of h. Okay, now let's see if we can know what the trace of h is. Trace of h is trace of phi transpose phi transpose inverse phi. And phi is a constant that we computed here, right? So I can compute this trace. So this is equal to trace of, I can take this phi here, right? It's trace of phi transpose times phi transpose inverse. So phi transpose times phi transpose inverse is identity. So it's trace of identity. What's the size of this identity? You know, this phi is m by n. And this n by m, and it's also m by m. So it's the size of this identity is m. So what's the trace of identity with size m? Is m. M was the number of nodes that we had, right? And conceptually, we knew that this quantity has something to do with the complexity. The more complex model have larger quantity di. Now we realize that it is in fact, this summation is in fact the number of nodes, which is the complexity of our RBF. You know, the larger the number of nodes are, the more complex the model. So basically, in RBF, the true error is empirical error minus n is sigma squared plus 2 sigma squared times m. So we want to choose the right complexity. You have to minimize the true error, not empirical error. But to minimize the true error, you can simply start with m equal to 1. Compute this quantity. Then m is equal to 2. Compute this quantity, and so on. At some point, you know, you see that this true error starts to increase. You know, it comes down, 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 and start to goes up with some m. That would be the optimum m. You shouldn't go further than that. You know, it should stop there. So basically, you can find the optimum model for RBF. Any question here? Yes.
If we just watch this error, we don't have to use cross-validation.
No, you don't need to do cross-validation because you can estimate the true error correctly just using your training set. Okay. So what about sigma? You know, sigma we assume has normal distribution, has been added to the true function, and it generates the observation. Now I have to compute the true error, and this true error has to do with the standard deviation of this noise. But what I have been given is just some observation. You know, just give me this xy. So what would be my sigma? So we don't have the sigma, we have to estimate it, right? So I have some observation, and I have some estimation, and over my data point, I can compute the, you know, standard deviation or compute the variance. But the thing is that if I replace the sigma here with this quantity, you know, this y hat by itself is a function of complexity. You know, the more complex, the less, the smaller this value. And the smaller this value. So in practice, in cases that we have this situation, we don't consider this y hat to be a function of complexity. We usually estimate the sigma with a low, with high bias and low variance estimation, say for example a line. So simply fit a line to the data, use the y hat of this linear function, compute the sigma, and consider the sigma constant over the estimation. Don't change it. You know, when you change the complexity of your model, don't change it. So really, sigma doesn't change with the complexity of the model. And we need to estimate it at some way. We need to estimate. The true estimation would be, according to the true model, but we don't know what the true model is. Let's assume that, a very high bias and low variance is our estimation at the beginning, set it there and then don't change it. This is usually what we do in practice. Okay, any question? So if you look at Schur, Schur was true error is empirical error minus constant plus 2 sigma squared this quantity. And we learned that this quantity is a function of complexity, right? So if I want to minimize error with respect to the complexity, instead I can minimize empirical error. This is constant plus 2 sigma squared di. This is function of complexity. This is justification behind regularization. One way of complexity control, which is very popular way, is regularization. Regularization means that instead of minimizing your training, your objective function, add a penalty to your objective function. And this penalty is a function of your complexity. It goes up where your complexity goes up. Okay? So regularization means that you have a function which you usually minimize, that's your objective function, add a penalty to this function, which is a function of complexity. So in this case, computing this derivative is hard. It was easy for RBF. In general, it's not easy. So let's altogether forget about estimating this derivative, but we just know that this derivative is a function of complexity, which has this form, and is going to be added to this form and produce a function of this form. So let's just add a function which increase by complexity. And there are other different type of penalty function that you can add here. Would be L2 norm, L1 norm, L2 plus L1 norm, all type of regularizer, okay? In all sort of model selection. It's called regularization, and we're going to see some particular case, one particular case of that, which is weight decay for neural network in next lecture.